On Monday and on Wednesday, we did several examples where we found the centroid for a one-dimensional body. And for a one-dimensional body, we know that the x and y coordinates of the centroid and the z coordinate, if applicable, is found by taking the integral of the centroid of a differentially small element integrated over the length of the element. All that divided by the integral of the length of the element, which this just means the total length of the element. However, this only applies for a one-dimensional body. So today, I'd like to find the centroid, but for a two-dimensional body. So my first question would be, if in one dimension, we are integrating over a length, in two dimensions, what do you think we will be integrating over?
In area?
Yeah, an area. So even though the integral is formulated pretty much following the same steps, we need to make sure, be aware that we are integrating over an area instead of over a length. And because we already know the theory behind it, let's just go straight to an example. And let's try an example where we all know what the final answer will be, just so that we know what to expect, okay? Let's try to find the coordinates for the centroid of this right triangle. So I'm going to draw a right triangle in the xy plane. And let's say that this right triangle has a base of b and a height of h. So we're going to keep this as generic as possible. So base of b, height of h. And we want to find the coordinates to the center of this right triangle. Now, we've already looked at centroids of triangles before, back when we were studying distributed loadings, right? So does anybody remember where the centroid of a triangle is located at?
Two-thirds of the total length of its base.
Yep. Yeah, it would be at two-thirds of you're measuring from one of the angles, or 1/3 of the distance if you're measuring from one of the sides. So ideally, my centroid should be located somewhere around here at a distance in the x coordinate of b/3 and a distance in the y coordinate at h/3. Then the reason we know this is, or the reason I want to work on this problem, even though we know the answer, is because we know what to expect. But you'll see that getting to that number actually takes a lot of work, okay? So let's start with this example. In this example, we'd like to find the x and the y coordinates of the centroid. I'll call them x bar and y bar. Now, because we are given this two-dimensional shape, typically when we're dealing with two-dimensional shapes, I would start by trying to find the limits of the area that we are going to integrate over. One way to look at two-dimensional shapes is see them as areas confined in between curves. In this case, we don't really have curves, we have straight lines, but that actually makes our work a little bit easier. So when you look at a two-dimensional shape on the XY plane, I'd like you to think of what are the boundaries of this shape. So for example, in this case, you notice that one of the boundaries of this shape is the line defined by the equation x equals 0. The equation x equals 0 is a vertical line, right, that passes through the point x equals 0. So that means that x equals 0 is one of our limits, okay? Another limit that we have is the equation y equals 0, because notice that y equals 0 is this horizontal line where y is 0 at every point, and y equals 0 is one of the boundaries of this triangle. So we have one boundary of the triangle, the other boundary of the triangle, and then we have a third boundary, which is this line. How do you think we can express this line in terms of x and y? Does anybody have any ideas on how we may try to express this boundary?
Can we express it by using the slope?
Yeah, that's right. Notice that this is just a linear equation. And just as a parenthesis, you know that linear equations will have the form y equals mx plus b, where m is the slope and b is the intercept. And in this case, it's actually pretty easy to find the slope, right? Because it's a linear equation, the slope will simply be the change in elevation over the change in horizontal displacement. So the change in y would be h2 minus h1, which is 0 minus h. So, and the change in x would be b minus 0. So we know that the slope of this line is simply negative h over b. We want to keep this form, so y equals slope times x plus b. And b is the intercept when x equals 0. In other words, the intercept in the y-axis. So for this line, when x equals 0, what does this line equal to? What does a point y equal to if it's in this line?
H.
H, correct. So this is our equation. Y equals minus h over bx plus h. And this would be one of the third line that delimits the boundary of this triangle. So I'm going to write it down here. This equation is y equals negative h over bx plus h. You can factor out some terms if you want, if it makes it easier for you, but I'm just going to leave it this way. Now, remember that when we are solving for our centroids, we need to make a choice on whether to integrate our equation in terms of dx or in terms of dy. And whatever choice whatever we pick, we will always want to make sure that all of our relationships, right, are in terms of one variable. So just to be on the safe side, in addition to having this equation for y, I'd like to have the same equation, but as a function of x. So if I were to take this equation, y equals negative h over bx plus h, and I were to solve for x, then I would get x equals negative b over h, y plus b. So these two are essentially the same equation, right? Except that in one, I solve for y, but if I were to solve for x, I would get this equation. They're the same equation, they represent the same line. The only reason I'm writing it both ways is because whenever it's time to make a choice on what integral operator to use, you want to make sure you have your equations in terms of y or in terms of x, whatever is available, okay? So let's go ahead and start solving this problem. Of course, this is just a preparation. Let's actually go ahead and try to solve this problem. We mentioned in our first couple of classes on this topic that the first step is to set a differential element. Now, in one-dimensional bodies, that differential element would have a length of dl. However, because we're dealing with two-dimensional bodies, we're going to have our differential element will have an area of dA, where dA represents a really small area. And this differential element dA is going to be located at an arbitrary location. And I'm going to call this arbitrary location just xy. So the step is the same. We set a differential element with an area dA, and we locate that differential element at an arbitrary point xy. So I'm going to choose a random point along this line xy. And here's the key thing. We have three lines that delimit my triangle. X equals 0, y equals 0, and x equals negative b h y plus b, which is this line. Why do you think my xy has to be on this line? And remember that eventually we're going to integrate. So why do you think xy needs to be on this line and cannot be on this line or this line? Any ideas? Let's give a clue. Remember, we are going to integrate over this area, all right? Does anybody remember what an integral represents in terms of plotting, in terms of graphs? Do you remember?
It's the area under a curve or a function.
That's correct. That's correct. So if we're integrating over this area and we know the integral will represent the area under a curve, it has to be this line. because my integral will give me the area under this curve, which is our sloped line. So that is why my arbitrary point xy has to be located in this line, because we're going to integrate, and to integrate we find the area under this curve. If we integrate over x equals 0, we really won't get an area. If we integrate over y equals 0, we'll get an area of 0. So we want to integrate over this entire shape. We want to make sure that our point xy lands or is located on this point. So we draw our arbitrary elements. And remember, this is differential analysis. So this will be a really tiny element, a really, really small element with an area dA. Let's just pretend that that's a straight element. This is a straight element. It's not curved like what I drew. So we have a tiny, tiny element with an area dA located at an arbitrary point xy. Now, you may be wondering, why am I making this element horizontal? Why not vertical? You can actually make the element whatever you want. It can be horizontal, it can be vertical. You'll still get to the correct answer. In this case, I'm just going to do the element horizontal, and we'll see what that means in just a second. So once we have set our differential element dA, the next step is to locate the centroid of this element. And remember that we're going to call the centroid of our differential element x squiggly and y squiggly. We're going to locate the centroid of this element as a function of x and y. In other words, we're going to locate x squiggly and y squiggly as functions of the location of the element. Now, I mentioned when we were doing one-dimensional bodies, we said that in one dimensions, this is actually really easy to do, because in one dimensions, because our differential element with length L in one dimensions is essentially just a point, then that means that x squiggly is equal to x, y squiggly is equal to y. But here, we're actually going to have something different. So let's see what that looks like. First, let me blow up this element here and show you what the element looks like if we were to zoom in an infinite amount. So if we're to zoom in, we get our differential element, okay, with a differential area dA. And we know that this point is x and y on your Cartesian coordinate plane. Now my question is, where do you think the centroid of this element is located?
In the center of the rectangle?
Yep. Look at this element. We have essentially a rectangular element. So my centroid will be located right at its center. So now here's my question. If we know that this coordinate point is x, right? In other words, we know that from the y-axis to this point, we have a distance of x, which means that my element has a length of x. What do you think is the coordinate of the centroid of the element?
Just 1/2 x.
Exactly, 1/2 x. I'll just call it x over 2. So the x coordinate of the element is x over 2. Therefore, I can say that my centroid x squiggly is equal to x over 2. Likewise, the y coordinate of the centroid, we know that this is actually a really, really small length dy. In fact, it's so small that we can treat this as simply a point, which means that the y coordinate of the centroid will simply be located at your y coordinate. Because you cannot really say, well, y plus 1/2 dy, because dy is actually so small that it's pretty much 0, right? So your y coordinate of the centroid will simply be y, okay? So we get that x squiggly equals x over 2, y squiggly equals y. And I mentioned on Monday, let's make sure that we don't skip this step, because when we're dealing with one dimensions, x squiggly equals x, y squiggly equals y, and we don't have to do any extra steps. But you can see here that in 2 dimensions, we actually have another expression for x squiggly. So we've located our centroid of this differential element. Now let's go to the next step. Remember, our third step is to express at express your differential element. And remember, before we used to use dl, but now we're going to use dA. So we want to express our differential element dA in terms of either dx or dy, whatever integral you want to use, okay? Dx or dy. Now here's my question. Because I chose to draw this element horizontally, that means that my element already has a differential length dy. Which of these two operators do you think we should use, dx or dy? Any ideas?
I think dx, since we drew our section horizontally.
So let me correct you here just a little bit. Because we drew our section horizontally, we already have a differential element that's dy. So because we already have a dy, then that's the integrand that we want to use. Does that make sense? So if we already have dy,
yeah.
we use dy. Okay?
Okay.
So yeah, so let's just go ahead and express it in terms of dy. So let's see. We have our element, and our element has an area dA. That's the area of this element. Based on the dimensions of the element, can anybody tell me what the area of this element is? Remember, it's a rectangle.
It would just be x times dy.
Yep, x times dy. Good. So we have our area, which is x times dy. But remember, we always want to make sure that our variables remain, our variables are all in terms of just one variable, right? Our equations are expressed in terms of one variable. So we have x, we know that x varies with y, so when we integrate, this will not be a constant. So if we're dealing with dy, we want to make sure that we express everything in terms of y, okay? And that's where we get to this line. Remember, we're going to integrate over this curve. And if you look at this curve, we know that in this curve, for any x coordinates, right, or any x coordinate can be found by multiplying negative bhy plus b. So we know from the curve that x equals negative bhy plus b. So I can write this differential area dA as simply x times dy, but x is equal to negative b over hy plus b. So negative bhy plus b. And all this, as you know, multiplied by dy. So we've expressed dA in terms of my dy term, and we've expressed everything in this equation in terms of y. Notice that now we only have y's, dy's, and constants. And that's the equation that we want to integrate, which leads us to our final step in this problem, which is to integrate. Now remember, setting up this integral is actually the hard part in this problem. Once we set up our integral, everything becomes plug and chug, right? So let's set up our integral. When we integrate, we know that we're going to integrate for the x coordinate of the centroid. This will be equal to this integral. So I'm just going to write it down here. And let's see what form this integral takes. I have the integral of x squiggly dA, but I already know that x squiggly equals x over 2. So I'm going to write the integral of x over 2 times dA, but I know that dA is equal to this entire expression. So I'm just going to write down the entire expression here. On the denominator, I have the integral of dA, and I know that dA is equal to this entire expression. So what else can we do? Remember that we are integrating over y, so we need to get rid of all of our x's. So I know that x here equals this entire expression, negative b over hy plus b. So I can just write it down because I have x and I have another x. This is just the same as x squared. So I can write down this integral as 1/2 of negative b over hy plus b squared times dy. And I have the same integral on the denominator, negative b over hy plus b dy. And finally, I can't forget about my limits of integration. Because we are integrating this equation over dy, in other words, we're looking at the curve as it moves in the y direction, we need to figure out what our limits of integration are. So for this entire curve can be found by looking at the area under this line from y equals 0 to y equals h. That means that my limits of integration will go from 0 to h. You can see that this integral actually just represents the area of this triangle. And hopefully you may have an idea, right? Does anybody know what the area of this triangle should be? Based on b and h?
1/2 b times h.
Yep, the area of this triangle will be 1/2 b times h. So we already know what this integral is going to give us. Like we know that this integral will give us 1/2 b times h. I'm still going to solve it anyway, just so that we can suffer a little bit, but we already know what answer we should expect, for at least for the denominator, 1/2 b times h. So let's go ahead and integrate. Hopefully you'll have some fond memories of your calculus class. Let's see, if we were to integrate this, I'm going to take out the 1/2 here because it's a constant. And then what do I have? I have the integral of b squared over h squared times y squared. Negative times negative is positive. So the integral of b squared over h squared times y squared should be equal to 1/3 of b squared over h squared times y to the power of 3. Let's see, I have the integral of twice this product, right? So this will be the integral of, I'm going to say -2, right? -2 b squared over h times y. The integral of -2 b squared over h times y should be an easy one. It's just negative b squared over h times y squared. And finally, I have the integral of b squared. And the integral of b squared should just be b squared y because b is a constant. So plus b squared y. And we know that this integral, or this result of the integral, is evaluated from 0 to h. On the denominator, what do I have? I have the integral of negative b over hy, so that should give me negative 1/2 b over hy squared. And I have the integral of b, and that should just be by. And of course, all this evaluated from 0 to h. And let's evaluate it. At 0 is easy, everything cancels out, but then we get h. So we have 1/2. Here I have 1/3 b squared over h squared times y to the power to y cubed, but y is h. So h cubed over h squared just gives us h. So this should be equal, right, to 1/3 b squared times h. Y equals h, right? So h squared over h is simply h. So this will be negative b squared times h. Y equals h. So this is just positive b squared times h. Hopefully you'll realize that our equation is slowly starting to simplify, right? You can see here that negative b squared h plus b squared h just cancels out. That's 0. On the denominator, I'm going to have negative 1/2 b over h. H squared over h is just h. So negative 1/2 b h. And here I have b times h plus b h. And finally, we can do a couple of final calculation steps. So this will give us 1/6 b squared h divided by bh minus 1/2 bh is just 1/2 bh. Notice that my h's cancel out. Notice that one of my b squareds in the denominator cancels out with one of the b squareds in the numerator. And this gives me 2/6 of b. And if we multiply by, I guess, 2/2, this will give me 1/3 of b. And that is the x coordinate of the centroid. is this the answer that we were expecting? So knowing what you know about triangles, right? Is this the answer that we're expecting? Yes, because the centroid is 1/3 of the distance measured from the wall, from the side, or 2/3 measured from the angle. And notice that here in the x coordinate, we get 1/3 of b, so it's just 1/3 along this x direction. Up to this point, we found the x coordinate. So up to this point, are there any questions? Any questions on how we integrate it? No? Okay. So if there are no more questions, I'd like for you to follow along as we find the y coordinate of the centroid. Okay? So let's go ahead and find the y coordinate of this centroid. Again, it can get tedious, but I think it's a really good practice for our integrals. Now, if I'm completely honest with you, I don't really have to integrate because I'm not a student. So this is even good practice for me as well. Like going over these integrals actually even helps me kind of get back into mathematical shape, if that's even a thing. So we know that our y coordinate will be the integral of y squiggly dA over integral of dA. We've already found from step number 2 that y squiggly equals y. So here, in place of y squiggly, all I have to do is write down y. We've also found from step number 3 that dA equals this expression. So I can write down the entire expression in place of dA. And we have the same integral in the denominator. And when it comes to limits of integration, the limits actually don't change because we're still integrating over dy. So 0 to h, 0 to h. We already know that the denominator will give us 1/2 bh. So let's just find out what this numerator gives us. So we first integrate negative b over hy squared. So the integral of negative b over hy squared should be negative 1/3 b over hy cubed. And then we integrate yb. So the integral of yb should be just 1/2 by squared. And all this is evaluated from 0 to h. In the denominator, we know that we'll just have 1/2 bh. Okay, so what does this give me? Let's see, at 0, everything cancels out. So at h, we had negative 1/3 b. Y is h, so h cubed over h is just h squared. So it's just negative 1/3 bh squared plus 1/2 bh squared. All this divided by 1/2 bh. Let's see, 1/2 minus 1/3. Let me just factor out the bh squared because I already know that these are constants, bh squared. And I get 1/2 minus 1/3. One half minus 1/3. I can multiply this by 3 over 3. I can multiply this by 2 over 3. And that should give me, I think, 1/6, right? Yes. So 1/2 minus 1/3 just gives me 1/6 bh squared over 1/2 bh. And hopefully you're starting to see the pattern here. 1/6 over 1/2 is just 2 over 6. B cancels out. And one of the h's cancel out, so we get 2/6 of h, or just 1/3 h. And we found the centroid in the y direction for this triangular shape. Hopefully we see that this is the answer that we were expecting, right? The centroid was going to be at 1/3 of b and at 1/3 of h. And the good thing about triangles is that the centroid will always be located at 1/3 the measured distance from any side. So if you take any side of a triangle and then you start measuring the distance normal to that side, perpendicular to that side, the centroid will always be at 1/3 of the distance between the side and the angle, okay? That's a law for all triangles. I've proved it using geometry with my geometry class, and we've proved it now using calculus with your class. So we have different proofs that the triangle's centroid is always going to be at 1/3 of the distance from the wall of the triangle. Up to this point, before we start another problem, are there any questions? If there are no questions, then I think it's a good thing, right? Because that means that hopefully we understand everything pretty well and we can start to tackle more complex problems. So let's go ahead and look at a different problem, okay? We've already dealt with two-dimensional bodies. And now I'd like to deal with two-dimensional bodies, but in polar coordinates. Now, polar coordinates was something that we tried out yesterday for a one-dimensional body. And it turns out that my static students haven't been exposed to polar coordinates before. That was a little bit surprising for me because I'm pretty sure that's something we should cover in any general math class, but it's okay because you have me. So we're gonna learn about polar coordinates if you haven't used them before. So let's talk first about polar coordinates. First off, this form of looking at points in space in terms of X, Y, and Z, in terms of three orthogonal axes, is what we call the Cartesian system. The Cartesian system named after René Descartes. Now the Cartesian system allows us to locate a point in space, and here we're just gonna use two dimensions just so that it's easier, allows us to locate a point in space by setting its horizontal displacement from an origin and its vertical displacement from an origin. Now, the horizontal displacement is what we call the x coordinate, and this vertical displacement is what we call the y coordinate. When you've dealt with vectors, you know that we can express a vector. Let's call any vector, let's call it vector f. We can express any vector in terms of its x component and its y component. And that is essentially the Cartesian system, allowing us to express points in space as functions or measurements from an origin through three orthogonal axes. Now, there are different ways to express this location. And the one that we're going to use today is called the polar coordinate system. And even though you may not have heard it before, you've actually already used the polar coordinate system before. So I'm going to draw my x and y axes just for reference. We're not really going to use them, but I'm going to draw them just for reference. And let's say that I want to locate any point in space. If I want to use the polar coordinate system, I can essentially see this point as a vector. So when a vector travels from the origin to a specific point, we can call this, let's call this vector r. We know that we can express this vector in terms of its x and y components, or another way we can express this vector is by looking at its magnitude and looking at its direction, which we usually define by the angle theta from the horizontal. So even though we know that a vector can be expressed with rectangular coordinates as simply fx plus fy, these are vector sums, okay, not scalar sums. We can also express your vector as simply the product, right, of the magnitude of the vector times the direction of the vector, where the direction is a unit vector, but essentially that just gives us the angle. So what I can do is, instead of expressing this point as a combination of a horizontal and vertical displacements, which I call x and y, I can express this point as a combination of the magnitude, right? The distance between the origin and that point, that's just the shortest distance, and the angle that the line from the origin to the point forms from the horizontal. So instead of using x and y coordinates, I can use radius and angle coordinates, r and theta coordinates. And that's essentially the polar coordinate system. It allows us to view elements in terms of r and theta rather than in terms of x and y. And I want to show you why polar coordinates are important and why it makes sense to learn them. You see, if we want to plot, and we actually did something similar to this on our previous example yesterday. If we were to want to find the area of a quarter circle, of course, let's say if you know the area of a circle, then you know that the area of a quarter circle should be just 1/4 of the area of a circle. However, let's say that you don't know that area and you want to find this area by integrating over this curve. First off, let's say that this circle has a radius of r, capital R. Okay, that's just the radius of the circle. Can anybody give me an equation in x and y, so in Cartesian coordinates, an x and y equation that relates or that helps us to identify this curve? In other words, if I were to say y is a function of x, what is that function equal to? Does anybody know? Let's see, we're looking at a circle, right? If we're looking at a circle, then we know that x squared plus y squared should give us r squared.
That'd be the square root of x squared.
The square root, right, of
x squared.
Isn't it 1 minus x squared or something?
Well, actually, it would be the radius, right? Radius squared minus x squared. I know what you're saying, and you're looking at it. If the radius were 1, then yes, it'd be the square root of 1 minus x squared. Anyway, this is my equation, okay? Now, if I want to find my area under this curve, I'm going to integrate this, right? And I'm going to integrate it over dx, so from 0 to r. This is going to be a bit of a nasty integral to solve, okay? And it becomes even more complicated when we start adding all of these other terms in our centroid equation. However, let's look at this in polar coordinates. In polar coordinates, can anybody guess what equation describes this line? Remember that polar coordinates tell us that any point in space can be found by looking at the radius, which is the distance from the origin to that point, and then theta. However, we have a curve here. So does anybody know perhaps what this line would look like in polar coordinates?
Cosine squared theta plus sine squared theta equals r theta. Or excuse me, r squared.
Okay.
Okay, let me correct that. Cosine squared theta plus sine squared theta equals r squared.
Okay. I'm gonna correct you just a little bit. I think what you mean is r cosine squared theta, r squared cosine squared theta, plus r squared sine squared theta equals, equals just r squared, okay?
Mm-hmm.
And this is pretty cool because first off, we already have a couple of identities here, right? We know that we can cancel out all of our r squareds, and we get that cosine squared theta plus sine squared theta equals 1, which is an identity that we already learned. But we also know, notice that our radius coordinates in no point in this line does that coordinate change. In other words, the distance from the origin to this line is always going to be capital R, right? So if I want to write an equation that describes this line, my equation will just be radius equals capital R. Now, which equation do you think will be easier to solve, to integrate over? Is it easier to integrate this, or is it easier to just integrate R equals a constant?
It's easier to integrate the constant.
Of course, right? Because the integral of a constant is just a constant times a variable. So that's why we use polar coordinates. It makes for, especially when we're dealing with circles, circular curves and fancy curves that require these harder integrals, polar coordinates will make our lives easier. And I will show you how they make our lives easier by solving an example that requires us to use polar coordinates, okay? So in this example, let's find the centroid of this quarter circle, okay? I'm only drawing my X and Y axes as reference because since we're gonna be using these equations for centroid, we're gonna have to switch between the two. And let's say that this circle has a radius of capital R. That means that the distance from the origin to any point in this line is gonna be capital R. I wanna find my X coordinate of the centroid and my Y coordinate of the centroid. However, because I'm dealing with a circle, I would like to use polar coordinates. So let's start. First, we know that the very first step is to set a differential element. And because this is an area as a two-dimensional body, our differential element will have a differential area of dA. Now, normally, we locate our differential element at an arbitrary point xy. However, now we are locating, because we're using polar coordinates, we're gonna locate our differential element at an arbitrary point r theta. So I'm gonna set my differential element. My differential element will be located at some random point in this curve, r theta. And now, because I'm using r and theta, notice if I were using x and y coordinates, my element has to be horizontal or it has to be vertical. However, because I'm using r and theta, my element should have a radius and an angle. Of course, remember my element is really, really, really small, right? It's so small, it has a tiny area dA that can't even be quantified numerically. So I've set my differential element. I've located it at an arbitrary point in the curve r theta. And r theta has to start from the origin because you have your radius r, and then whatever your displacement angle theta. Once I set my differential element, I can then locate the centroid of the element, which we know is called x squiggly, y squiggly. However, because we're using polar coordinates, we're gonna locate x squiggly and y squiggly as a function of r and theta. So let's see what that looks like. First off, let's look at this triangular element, right, that I've drawn. I'm gonna blow it up here just for, I'm gonna exaggerate its dimensions. But essentially my element looks like this really, really small triangle. It's really, really small, so small that we can't even quantify this area. However, we know a couple of things about this element, right? First off, does anybody know, if we're using r and theta as our guides, what do you think is this distance, right? This length of the triangle, this altitude. What do you think is the distance from 0 to the point r theta?
R.
Just r, right? So we know that our triangle will have an altitude of r, but it's a really small triangle with a very, very small area. So what do you think this very, very, very small area would be equal to? Remember there we go, right? R d theta, right? Remember that the arc length of a circle is found by multiplying the radius times the angle of that arc length. So in this case, the angle of this triangular section is a tiny angle d theta. So it's a really, really small angle. Therefore, the arc length of this segment should be just r d theta. Now, because this is a differential element, is really, really, really small element, I can actually treat this element like if it were a triangle. And we already know that if this element is a triangle, where in the triangle is this centroid going to be located at? Where do you think?
One-third R.
Yep. At 1/3 from any wall. In this case, oh, this is definitely not 1/3. Let's just imagine that was 1/3. In this case, 1/3 measured from the wall of the triangle. So let's write that in terms of our coordinates. In this case, right, we know that this centroid, right, will be located at 1/3 if we measure it from the wall, or 2/3 if we measure it from the angle. So this centroid should have coordinates of 2/3 r and theta, because this element, this point in the triangle is r theta. Therefore, this centroid should be 2/3 r theta. So we know that our centroid is located in polar coordinates at 2/3 r theta. However, our x squiggly and y squiggly are still Cartesian coordinates. So we still need to find a way to relate these Cartesian coordinates, x squiggly and y squiggly, to our polar coordinates r and theta. However, this is actually easier than you think, right? If we're looking at a vector with a magnitude r and an angle theta, what do you think is the x component of that vector?
R cosine theta.
That's correct. And in this case, if I'm looking at a vector, right, a position vector with a magnitude of 2/3 r and an angle theta, then we know that our x coordinate of that point should be simply the magnitude 2/3 r times cosine of the angle theta. Likewise, what do you think the y coordinates of the centroid of this element will be? Following that same line of thought.
2/3 r sine theta.
Yep. So we've located x squiggly and y squiggly as functions of r and theta. That was step number 2. Not too bad. As long as we understand the relationship between polar coordinates and Cartesian coordinates, this is actually a pretty easy step to take. Then we will express our area, dA, in terms of either dr or d theta, right? One of the two. Now, we mentioned that there's a reason why we chose dy over dx in the previous exercise, because we already had a differential element dy. So we chose dy as our integrand. In this case, would we use, based on this differential element, would we use dr or d theta as our integration?
D theta.
Yeah, d theta. So we want to express our area dA in terms of d theta. Now, of course, this is a triangle. The area of a triangle, as you may already know, the area of a triangle, dA, is simply equal to base times height over 2, 1/2 base times height. So the area of this triangle should be equal to 1/2 of the base, in this case, my base is r d theta, times my height, which is r. So r times r is just r squared d theta. So my area dA is simply 1/2 r squared d theta. Up to this point, are there any questions? All right, so if there aren't any questions, let's go ahead and solve the final and easiest step.
Could you explain the area formula one more time for dA?
Yep, of course. So first off, this is a triangle, right? We know that the area of a triangle is 1/2 of the base times the height of the triangle, right? So this triangle, right, the area of this triangle is 1/2 BH. Now, when it comes to this differential element, remember, this is a really, really, really small element, okay? So because it's a small element, the size and the altitude are the same. So we have r, and here we have r d theta as our base. So the area will be 1/2 this times this.
Could you move the paper up just a bit? I can't see the bottom. Thank you.
So this element is essentially a triangle, right? We're treating it like a triangle with a base r d theta and a height r, which is what we already drew here.
Okay, that makes sense. Thank you.
All right, no problem. So let's go ahead and go to the easier step in this problem. And you'll see when we use polar coordinates, you'll see how easy this step becomes, right? The final step in the problem, as we already are aware or familiar with, is to integrate. You may have noticed that every time I write integrate, I write an exclamation mark after it. I'm trying to use subliminal techniques to get you excited about integration. So hopefully whenever you see an integral, you'll be like, for some reason, I'm happy. So we'll see if that works. I'm not very good with psychology or psychiatry, so we'll see if all that works. But for now, remember, integrating is fun because it's easy. At least in this context, it's actually easy. So let's go ahead and integrate. We know that the x coordinate of my centroid is the integral of x squiggly dA over the integral of dA. So what do we have? We've already found from step number 2 that x squiggly equals 2/3 r cosine theta. So here we have the integral of 2/3 r cosine theta. This is starting to look like it's not going to be so easy, but we'll see. And then we have this multiplied by dA. And we already found from step number 3 that dA is just 1/2 r squared d theta. So we multiply this by 1/2 r squared d theta. In the denominator, we have the integral of dA, so that's just the integral of 1/2 r squared d theta. Now, you may already know this, right? But this is a quarter circle. And we know that the area of a circle is pi r squared. So that means that this integral, right, should give us pi r squared divided by 4 because it's a quarter circle. But let's integrate it anyway, just to make sure. First off, how can you express this curve, right, in terms of r and theta? Does anybody remember, we already did the same thing for a similar curve. Do you remember if the radius of the circle is capital R, how do you express this curve in terms of theta? Or sorry, in terms of r and theta? Is there anything that theta does that changes the value of r?
R changes as theta goes to 90 degrees.
Does r change? Remember, r is the distance between the origin and the line, just a straight distance.
It would be r d theta, right?
Actually, if I want to just plot this curve, remember, this is a curve. Notice that theta can change all at once, but my radius still is constant, right? My radius doesn't change. The distance between the origin and this point is r. The distance between the origin and this point is r. That doesn't change, right? Because it's a circle.
So just the integral of r?
Yeah, exactly. In this case, my equation is just r equals the radius of the circle, which I just call capital R. It's a constant, and that's kind of what I want to get at. R is a constant. So now let's look at this integral. If r is a constant and that constant is capital R, then can we take it out of the integral?
Yes.
Yeah, because it's a constant. All right, so I'm going to take my integral, my constants out of this integral. Let's see. I have 2/3, I'm going to take it out. I have 1/2, I'm going to take it out. That gives me 1/3. And then I have r times r squared, that's r cubed. I'm going to take it out of my integral. So I get r cubed. And remember that my equation said that r equals capital R. So I'm just going to replace that capital R here. So get r cubed times the integral of cosine theta d theta. What about our limits of integration? Here, remember, we want to integrate as d theta changes. So here, the angle changes from what to what in this curve?
From 0 to pi.
0 to pi over 2, right? Remember, pi is a semicircle. So, yep, 0 to pi over 2. So we get 0 to pi over 2. That's our limits of integration. The denominator, again, I can take out the constants. So I'm going to have 1/2 r squared, integral from 0 to pi over 2 of d theta. And now, instead of dealing with a nasty integral like we had in the very first problem we did on Monday, we have a pretty simple integral. Get 1/3 of r cubed. What's the integral of cosine theta, d theta?
Sine theta.
Sine theta, yeah. Well, 1/3 r cubed. Sine theta evaluated from 0 to pi over 2. All that divided by 1/2 r squared. What's the integral of d theta?
Theta.
Theta evaluated from 0 to pi over 2. And this actually is pretty easy, right? We know that the sine of pi over 2 is 1. The sine of 0 is 0. So this will just be 1/3 r cubed. We know that, well, here there's no sign. We just evaluate theta equals pi over 2, theta equals 0. So this will be just 1/2 r squared pi over 2. We can start canceling things out, right? Our r squared cancels with 2 of these r cubes. We're going to have 4 here, other denominator 3. Okay, so what does it give me? Let's see. I'm going to have 2 times 2. I'm going to move it up. So it will be 4 times r divided by 3 times pi. And this is the x coordinate of the centroid of that quarter circle. We can do the same thing for my y coordinate. Y bar equals y squiggly dA over integral dA. We found from step number 2 that y bar is 2/3 r sine theta. So I'm going to write it down. Integral of 2/3 r sine theta. And we found from step number 3 that dA equals 1/2 r squared d theta. 1/2 r squared d theta. Same simplifications, right? We know that r is a constant, which is capital R, the radius of the circle. We can take it out of our integrals. 2/3, 1/2, we're going to all take all that out. So this gives me 1/3 r cubed. The integral from 0 to pi over 2 sine theta d theta divided by 1/2 r squared integral from 0 to pi over 2 d theta. Can anybody tell me what the integral of sine theta d theta is?
Minus cosine theta.
Yep, negative cosine theta, that's correct. Negative cosine theta from 0 to pi over 2. And we know this will actually be the same thing, right? This will just be pi r squared over 4. So just write it down. Pi r squared divided by 4. All right, so what do we have? Cosine of pi over 2 is 0. So we get negative 0 minus negative cosine of 0, which is 1. So minus negative 1 is just positive 1. So this is just 1/3 r cubed divided by pi r squared over 4. We cancel out some of our terms and we get, once again, 4r divided by 3 pi. And that's the y coordinate of this centroid. At this point, are there any questions? It's a lot of work. It's a lot of work to find a centroid, but I mean, it is what it is, really. So we've solved two-dimensional problems, one in rectangular and one in Cartesian and one in polar coordinates. And on the previous 2 classes, we solved 2 one-dimensional problems, one in Cartesian coordinates, one in polar coordinates. My plan would be to continue solving these problems and hopefully get into some three-dimensional problems before we finish this topic. We're going to finish this topic at the end of next week. So we're going to get a lot more chance to work on other examples. Any questions before we end this class?
So if you're looking to find the centroid under, or the centroid of any curve in the first quadrant, when you begin to look at DA, would you always take into consideration DA being similar to a triangle?
If you're using polar coordinates, it has to be a triangle.
Okay.
And then if you're using Cartesian coordinates, it has to be a rectangle.
Okay.
Could you just quickly go back to the solution to y? Okay, thank you.
Circles are very symmetrical. So X bar and Y bar should be the same. And you can see it here, right? They are the same. Okay, so in this example, we are given this shape. It kind of looks like a triangle, but it's not really a triangle. This is supposed to be a curve, like a parabola. And we want to find the centroid of the shape that is essentially bounded by these three lines. Okay, so that's the first thing we want to find, the centroid. Now, because we're dealing in two dimensions, you may recall from the other two-dimensional problems that we want to define the limits of this area. So you can see that this area is bounded by three curves, right? The first one, the easiest one to find, is the curve y equals 0, right? The line y equals 0 forms the bottom bound of this shape. So we have the line y equals 0. Then we can see the line x equals 1 that serves as another boundary for this curve. And of course, the third boundary for this curve is, or for the shape, is the curve y equals x squared, which gives it its parabolic shape. So y equals x squared. So that's the information we're given, right? We're given this shape. We want to find the centroid of this shape. Now, a problem like this, it's better to just deal with it in Cartesian coordinates. There's no real need to switch to polar coordinates right now. So let's remain in Cartesian coordinates. You may recall that the first step in solving a problem like this is to set a differential element. Now, in one dimensions, this differential element would have had a differential length dl. However, we are dealing with two dimensions, so our differential element will have a differential length dA. Now, we're going to place this differential element at some arbitrary location xy. Okay, so this element dA will be set at a location xy, and that location xy will have to be somewhere in this curve. You may recall that the reason we are setting xy in this curve is because we're going to have to integrate. And if we integrate over the line y equals 0, we'll get an integral of 0. And if we integrate over the line x equals 1, we won't get any result. So we always want to make sure that our element is located at some arbitrary location in the curve that we're going to integrate over. Okay, so let's start. We first set our differential element, and I am going to draw my element here. It's a really tiny, very thin element. You can see that even though it has a discernible height, the width of this element is actually going to be very thin. This element will be located on this curve at a point x equals y, which is some arbitrary point. So that's the first step, right? Coming up with this differential element, placing it at an arbitrary location. Then we are going to locate the centroid of this element, right? And we said that the centroid of this tiny element is called x squiggly, y squiggly. By the way, nobody calls this squiggly. I just call it that because I feel that it's like a squiggly line. I hope this is obvious, but don't go to your other professors and say X squiggly because they won't have any idea what you're talking about, okay? So we're gonna locate this X squiggly, Y squiggly, which is the centroid of this element. And we're gonna locate the coordinates of that centroid in terms of X and Y. So in terms of X and Y. And what I mean by that is this differential element has a centroid, and you know that centroid is here at the center of this rectangle. So we want to know what are those coordinates, right? The coordinates of this centroid, I'm just going to draw it here. The coordinates of the centroid of this tiny rectangular element are X squiggly, Y squiggly. But we want to express these X squiggly and Y squiggly as functions of this point X and Y. So in other words, the idea is, how is the X coordinate for this, how is this X squiggly coordinate related to this X coordinate? How is this Y squiggly coordinate related to this Y coordinate? So in order to study that, let me draw this element. I'm going to try to exaggerate it a little bit. We have the element here. We know that this is a differential element. So it's a very, very thin element. And because it's very, very thin, the thickness of the element is simply an infinitesimally small thickness that I'm going to call dx. However, we don't need to say that the height is infinitesimally small because it's not. It's a discernible physical height. Now, you know that this point, it lies at coordinates x, y, the point on top of the element. So what do you think is this height of the rectangle? We know the width, the base is dx. What about the height? Does anybody know what the height would be in terms of these coordinates?
Would it be x squared?
Yes, right? It would be y. And like you said, it's definitely x squared. So let me just take it step by step, right? You are definitely correct, but let's just start step by step. This vertical coordinate is y, right? Because from here to here, you have a distance of y because this is the y position. However, Hugo is right? If you look at the curve, you know that for every y, you have an x squared, right? Y equals x squared. So we know that this is y, but we also know that y equals x squared. So because you already mentioned it, let me just write it down here so we can remember it. Y equals x squared. So because this is y, that means that this is also x squared. Now we want to locate x squiggly and y squiggly in terms of x and y. So I'm going to start with x squiggly. Remember that this is a very, very thin element. So I'm exaggerating the dimensions here, but in fact, it's so thin that you can actually picture it as if it were just a line. So if this were just a line, you know that the centroid is located at the center here at coordinates x squiggly, y squiggly. How do you think, or what do you think is the difference, if any, between the x coordinate to the centroid and the x coordinate to that point? In other words, if you were to measure the distance from the y-axis to the centroid, and then measure the distance from the y-axis to my point x, these two distances, how are they related?
Will it just be x?
Yeah, they're the same distance, right? So x squiggly here is just equal to x, no change here. However, we can't say the same for y squiggly. When you measure the distance y, you are measuring from the x-axis all the way up to this point xy. But then if I'm measuring from the x-axis all the way up to the centroid, what do you think that distance would be in terms of y?
It would just be 1/2 y.
That's correct. So we've located our x and y's in terms of our x squiggly and y squigglies in terms of our x and y's. So far, good job. But now there's a little bit more work that we can do, right? One recommendation I would give is when you draw your element, we already said that we have a choice of drawing our element vertically or drawing it horizontally. Now I chose to draw it vertically. And if I draw it vertically, that means that my horizontal distance will be my infinitesimal operator dx. That should give us a clue that our integral should be expressed in terms of dx. And if our integral will be expressed in terms of dx, then ideally you want these two variables to be always in terms of x. So we know that x squiggly equals x. There's no change required there. However, y squiggly equals 1/2 y. But if we want to express y squiggly as a function of x, how do you think we can turn this 1/2 y into a function of x?
You just plug in the value of y, which is x squared.
There we go. So this tells us that y squiggly is just 1/2 x squared. And the reason I'm doing this now, normally I wait until the third step to do this, but because we already established this relationship, we can just go ahead and get this step out of the way now so that it can make our calculations easier in the future. The third step into solving this problem is to express our differential area dA in terms of dx. And the reason I chose dx is because my differential element is vertical, and therefore my x distance will be our differential operator. If I would have chosen a horizontal element with a really tiny vertical distance dy, then I would be expressing my dA in terms of dy. But because we are dealing with dx, we will express it in dx. So we have our differential element here. It's a rectangle. It's a rectangle with dimensions y and dx. So what do you think is the area, dA, of this rectangle?
Y dx?
That's correct, y dx. And of course, because we want to express everything in terms of x, we know that y equals x squared. So the area is simply x squared
Dx.
dx. So we have our first three steps. And like we said, these are the harder steps, right? Setting up the integral. They're not the longer steps, but definitely the hardest ones. Once we have our integral, our final step is to integrate. And from here, we can apply our knowledge of calculus to essentially solve this problem. So we know that the coordinate to the centroid x bar is simply the integral of x squiggly dA over the integral of dA. Now, we already know that x squiggly equals x. So I'm going to say that x bar equals the integral, and x squiggly equals x, so just of x, times dA. But I know that dA from step number 3 equals x squared dx. X times x squared is just x cubed. So I'll just write integral of x cubed dx. Now we can't forget our limits of integration, right? We are integrating over dx, which means that our limits will go from the lowest x value to the highest x value. In this case, my lowest x value is at the origin where x equals 0. And my highest x value is at the end of this shape which has an x coordinate of 1. That means that we're going to integrate from 0 to 1. Those are our limits of integration. On the denominator, we have the integral of dA, and we know from step number 3 that dA equals x squared dx. And the limits of integration are the same, from 0 to 1, x squared dx. And from here, it's just integrating, which we already know how to do, right? The integral of x cubed should be 1/4 x to the power of 4, evaluated from 0 to 1. And the integral of x squared should be 1/3 x to the power of 3, also evaluated from 0 to 1. And this is actually a pretty easy one, right? You can see here that this is x equals 1 minus x equals 0. Zeros don't really matter here. So x equals 1. So we have 1/4 divided by 1/3, which is simply 3/4, or 0.75. So that is the x coordinate for this point. Any questions up to this point before we continue?
Yeah, I'm a little confused on how you got your x squiggly. I mean, I understand how you got your y squiggly. You just took the half of y, but how'd you get your x squiggly?
So remember, x squiggly is the coordinate of the x location of the centroid, right?
Okay.
So that if it's the x coordinate, that means the distance to the y-axis, right?
Okay.
Now we want to express this distance. This distance is x squiggly. we want to express it as a function of this distance, which we call x, right? So this is x, right? This distance from here to here is x. Now this is a completely vertical element, which means that the x distance at any point should be the same, right? So x squiggly and x, as you can see here, they have the same distance. So that's why x squiggly equals x.
Okay.
Okay. You can see that that's not the case for y, right? For y, we have actually double the distance to the point compared to the centroid. Does that make sense?
Yeah, yeah.
Awesome. Y bar, again, y bar, integral of y squiggly dA over integral of dA. We know from step number 2 that y squiggly is 1/2 x squared. So I'll just write 1/2 x squared. I'm gonna write x squared later. And we know that dA from step number 3 is just x squared dx. So x squared times x squared is x to the power of 4 dx. Limits of integration don't change from 0 to 1. All this divided by the integral of dA. Now we already solved the integral of dA, right? It's just gonna be 1/3. So I'm just gonna write it as 1/3. I'm not gonna resolve it because we already know the answer here. Okay, we integrate this, pretty simple integral as well. If I'm looking at this correctly, the integral should be 1 over 2 times 5, 1 over 10 x to the power of 5, evaluated from 0 to 1, divided by 1 over 3. This is just 1 to the power of 5 minus 0 to the power of 5, so that's just 1. So 1/10 over 1/3 is 3/10, and 3/10 is just 0.3. Any questions on how we solve this problem? I know I'm kind of rushing on purpose because I really want to get to 9.14, but are there any questions with this problem? All right, if there are no questions, let's do an actual homework problem. Now, I've already received more than one student asking me about 9.14. So hopefully when we solve it here, it should clear up some of our doubts with this problem. So if we look at 9.14, we have a similar looking curve. However, the curve is given to us a little bit differently. In this case, my curve is actually bounded not by the x and y axes, but rather it's bounded by the following lines. This shape is bounded by the following curves. Now we know that this curve has an equation of y equals 4 minus 1/16 x squared. And we know that the horizontal length of this shape is 8 meters. Now from this equation, we can tell that the vertical distance is 4 meters. And our shape is bounded by these 3 curves. In other words, this is my shape, not this, but this. And we want to find the centroid of that shape. In other words, we were asked once again to locate the centroid in this shape. So we're going to locate x and y, x bar and y bar. Because we're dealing with a 2-dimensional problem, I'm just gonna always repeat, make sure you know your limits of your area. And I'm gonna try to let you attempt this one. So we know that there are 3 lines, 3 curves that bound this shape. This curve is already given to us. It's y equals 4 minus 1/16 x squared. So how would you express the other 2 curves that bound this shape? How would you express them?
You could say y is equal to 4 and then x is equal to 8.
Yeah, that's correct. So we get y is equal to 4 and x is equal to, x is equal to 8. So essentially this 2-dimensional body is bounded by the curves y equals 4 minus 1/16 x squared, y equals 4, and x equals 8. Those are the 3 curves that bound this element. Then, like I said, it's important to know the limits of your area because these will help us to set up our integral. Now, hopefully you will be able to see how this problem actually becomes a bit of a problem to solve because In every other issue that we've had, we've been bounded by the X or the Y axis. So in here, we're bounded by the X axis. So it's a little bit easier to set up our coordinates and locations. Here, we're not bounded by the X nor the Y axes. Therefore, we're going to have to do a little bit of extra work in order to solve this problem. So let's start. We know that the first step is to set a differential element. This is a two-dimensional problem. So my differential element will have a small differential area dA, and we're going to locate that element at an arbitrary location xy. Now here, things become interesting. My issue with bounding or locating my xy in this curve is that if I integrate over a straight line, I just get the area of a rectangle, and I don't want that. Therefore, I'm going to make a judgment call and say that my xy should most likely be located still on this curve. And you'll notice that when we find our x squigglies and y squigglies, that is going to make up for any differences between this shape and this shape. So we'll see them in just a second. So let's just go over this problem step by step. First, we set a differential element dA that is located at my point x, y, okay? And we already said that xy will be in this curve. So my point xy, wait a minute, my cat is eating my, my headphones. All right, I'm gonna have to ask for a minute of your time. Can anyone hear me? Let's see, can anybody hear me now? Hello.
Yeah, we can hear you. Just
Sorry, my cat is eating my switch.
We saw the shadow of the cat. It was funny.
Yeah. So I'm gonna have to let go of my headphones and just use my computer's mic. Anyway, let's go back. All right. So we set a differential element dA at xy. So this is my point, arbitrary point xy. My differential element has to be located right in my shape. So this is my differential element, okay? Now, step number 2.
Quick question, Professor, before you go on. Why would it not be going down?
Because remember that the differential element, remember that the differential element is part of this shape, right? So the element has to be located on the shape itself. So this is my shape. If I were to set my differential element all the way down here, I would be getting the centroid for this area. But I don't want the centroid for this area, I want this shape. Okay?
Oh, okay. I see what you're saying. Okay.
So the element has to be located in inside the shape, okay? Inside your area.
Okay.
All right. So we set our differential element dA located at an arbitrary location xy. And now the next step is going to be to locate x squiggly and y squiggly. So locate the centroid of this element, which we know we call x squiggly and y squiggly. And we know that we want to locate x squiggly and y squiggly always as functions of x and y. So as functions of x and y. Okay? So here's where things may get a little bit complicated for this problem. But you'll notice that it's actually just math, what's going on. So let me just draw my element. Here's my differential element. And if you look at this diagram, we know that this differential element is not going to be on my x-axis. So I'm just going to draw my x-axis here at the bottom. All right, let's just say this is my x-axis. And here's my element. Just draw my curve here. I know a couple of things of this element. I know that the bottom of this element, the point in the bottom of this element has coordinates x, comma, y. what do you think the coordinates of the top of the element are? What do you think? Does x change when you move from the bottom to the top? Does the x coordinate change?
No.
No. Okay, so the top of the element should have coordinates x. However, here we have coordinates of y, right? What do you think the coordinates are up here? What is the y coordinate up here?
4 minus y.
Well, just the y coordinate, right? Would be just 4.
Oh,
Right?
4, sorry.
Because this is the line y equals 4, which means that any point in this line, y will be equal to 4. So the top has coordinates x4, the bottom has coordinates xy. But I like what you said, Ray, because now we can use that information to find the dimensions of the element. If the bottom is y and the top is 4, what do you think is this length? This vertical length?
4 minus y.
That's correct. So this length is 4 minus y. Okay? We know that the width is our tiny differential length dx. And now we want to find the coordinates to the centroid of this rectangle. That's a centroid. So let's start with the easy one, the x coordinate, or x squiggly. Is there any difference in the x coordinate between the centroid and the bottom point, which is xy?
No.
Okay, so x squiggly, if there's no difference, x squiggly should just be equal to x, right? Because this is a vertical element. Does that make sense?
Yes, yeah.
Okay, but now let's look at the y coordinate. This is my point y. This is the centroid, this is y squiggly, and this is 4. Now y squiggly lies somewhere in between y and 4, right?
Yeah.
Based on the size of this rectangle, where do you think y squiggly lies relative to the rectangle only?
Is it 4 minus y over 2?
Exactly, right? So relative to the rectangle,
Okay.
my y squiggly is going to be at 4 minus y over 2. However, relative to the x-axis, because that's really what we want, my y squiggly will be equal to, well, we know that this is y. So my y squiggly will be equal to y plus 4 minus y over 2. So I'm just going to write down y plus 4 minus y over 2. Now, of course, you notice that this is actually just the midpoint between y and 4, right? So if you were to just solve this equation, you would get that y squiggly in this case would be equal to 1/2 y plus 4. Yeah, that's true. Because y plus, what again? Yeah, y plus 4 minus y over 2. Yes, it'll be 1/2 y plus 4, which is simply the midpoint between y and 4. Up to this point, does everything make sense? Or do we need more explanation on how we found the x squiggly and the y squiggly?
That makes complete sense now.
All right, good. I'm happy it does. It's a tough one to figure out, right? But
Yeah.
hopefully once you know this, you'll be able to solve all the other problems with relative ease.
Quick question, Professor. Why
Okay.
the like, could you know why is 4 minus 16x squared? How come that doesn't come into play when we're figuring out the y?
Remember that 4 minus 16x squared is only related to this curve, right?
Mm-hmm.
But here, we're not looking at the curve anymore. We know that this point xy is somewhere in this curve, and we will use that whenever we're converting this y into an x function. But right now, all we're looking at is at the distance between the x-axis and the centroid. That's all we care about right now. So
Okay,
right now, we care about the curve, okay?
So technically that y plus 4, that y would be y minus 16x squared.
Technically, this would be 1/2, and this would be 4 minus 1/16 x squared. So
Okay, yeah, that's what I was saying. Okay,
Yeah.
gotcha.
All right, does that make sense?
Mm-hmm. Yes.
Okay. So finally, I have about a minute left because I have a fluids class after this, so let's just be quick. Finally, the third step would be to express your area, dA, in terms of dx. I'm not even going to use different colors this time. Express dA in terms of dx, okay? And in this case, if you look at this rectangle, we already have the length and the width. So what's the area, dA?
Oh, it's gonna be dx times 4, right?
Dx times actually this height, right?
I'm sorry, 4 minus y.
Thank you. So it's 4 minus y dx. Now, I ran out of time. So in order to finish this problem, remember, you want to express all your y's in terms of x. And the way you do that is by using 4 minus 1/16 x squared. So you express this y in terms of x, you express this y in terms of x, and then finally your last step will be to integrate. Since this is a homework problem, I guess I don't feel that bad that we didn't finish it. You can finish it yourselves right now, but hopefully this gave you a bit of an idea on how to go on with this problem. So any final questions before we leave?
No questions.
All right,
No,
good.
Professor, thank you.
So